So hi everyone, and welcome to today's Saturday Investigate. And so my name's Molly, and I'm here from the University of Nebraska State Museum with Cindy, who's going to be presenting today. And today we'll be exploring the topic Quaking Planet and looking at plate tectonics and earthquakes. So if you have any questions during the presentation, please feel free to put them in the chat window on Zoom. The chat window looks like a little chat bubble. Just click on it to type in your question. And if you're joining us on Facebook, you can post questions in the thread. We'll be monitoring both chats and can ask your questions as we go. So thank you all again for joining us this morning for Quaking Planet, and I'll pass it over to Cindy.
All right, quaking planets. That's what we're talking about today. And those of you that were with us last April, we were talking about the amazing Earth, and we did an activity where we looked at what the structure of the Earth is. So if you were with us, or if you know, tell me the three parts, put it in the chat box, tell me the three things that the Earth is, three parts to the Earth. Oh, there's somebody from Fairbury, excellent. Three parts of the Earth. Okay, I'm not seeing any answers. Think about this. You think about the Earth, what's in the outside round, and then what goes inside and what's deeper inside. All right, now we've got it. The crust, the mantle, and the core. And you know what? Before we go any further, I forgot to tell you that we have a lot of these activities and things posted on our Facebook page, and I'll try to remember to pull that screen up at the end of the program so you can see the email or the web page. But one activity we're doing here is going to be posted, and another new different activity that I'm not doing here is going to be posted, but it's all tied to the same thing, which is talking about the Earth. And we talked about the crust, the mantle, and the core last time. And that one way of looking at that is that it is the chemistry, the chemical layers of the Earth. The crust being igneous rocks, sedimentary, metamorphic, all the three types of rocks. And the mantle consisting of magnesium and iron. And then the core of nickel and iron. So those are the chemistry, the chemical layers of the Earth. But there's another way to look at the layers of the Earth. And let me share this with you. Okay, well, there's our screen, our web page information, and oops, okay, that's the chemical layers. So you can see the crust, the mantle, and the core. But some scientists prefer to think about it because of the work that they do, the nature of the work that they do. They think about it in a structural way, in how do those materials react or respond. So they've come up with the crust and the upper part of the mantle being called the lithosphere. Litho means rock. Rock is rigid. So the crust and the upper mantle is rigid, and it's called the lithosphere. And we're going to be using that term today, the lithosphere. Underneath the lithosphere is the asthenosphere. That's different. If you remember, last month we talked about the mantle having a different kind of texture to it. It's one layer. And the asthenosphere is this silly putty-like substance. So you can see how plastic and mobile it is. I mean, I certainly can't pour it. It's not a liquid, no liquid. But it's not rigid either, like a rock. There's no way I'm going to be moving a rock around like this. Okay, so this is really, really flexible. Flexible plastics, another word they use, a mobile. It's very different. That's the asthenosphere, and that's really important. Okay, so we've got that rigid crust, the lithosphere, on top of this mobile, plastic, flexible asthenosphere. Now I want to show you one more image here. And okay, so in the 1800s, explorers are going around the world. They're making maps, and a number of scientists were looking at this world map that they'd come up with. And they noticed something interesting about South America and Africa. Put in the chat box what you think is kind of interesting. What do you notice about South America and Africa. What ideas do you have when you look at those two continents? I wonder if you're going to come up with the same thing that explorers and scientists discovered, 1800s, late 1800s, and more recently. Let's see what we got here. Oh, goodness. Yes, they look like they could fit together. Okay, so there's a scientist called Wegener, and Wegener, he noticed that, and he came up with some evidence to support this idea that once they fit together. And when he came up with that idea, he told everybody else about it, and they said, okay, yeah, this doesn't make sense. The earth is rigid, it's solid, it doesn't move. How could these two fit together? Well, he came up with evidence, and if you go to our webpage and check out, there is a, I think it's called the tectonic plate puzzle. It's based on the fossils. It's based on the evidence that Wegener found. And you too can help prove that South America and Africa were once joined. Well, this was in the early 1900s. In the 1960s, we got a lot more equipment, a lot more data was coming in. They were able to look at the seafloor, and they made some discoveries, and they started looking back at Wegener's continental drift idea, where the continents moved. But they expanded on it, and they came up with a new theory called plate tectonics. And this plate tectonics, they had a way that these plates or the continents could move. And we're going to talk about that today. So remember that lithosphere, that hard crust on top of the softer asthenosphere. They think that the crust is broken up into plates, and these plates can move around on this asthenosphere. Okay. They think there's 7 plates, large ones, and a whole bunch of small ones. So let's look at what plates they've come up with and why they think this. So the first plate I'm going to show you is the Antarctic plate. And I'm going to start with this globe here because it's a lot easier to see Antarctica if we look at the globe. All right, so I've got this North American continent here. You can see that. Let's make sure the light's right. And then here's South America, okay? And we're going all the way to the South Pole. And look, there's Antarctica. Look how round it is. It's a pretty round continent. You don't realize it because most of the time we don't see it this way unless we're holding a globe. So we've got this Antarctica, and it is a plate unto itself. It's got continent and oceanic crust. But it's one big plate. And I'm going to put my puzzle piece here on my board. Let me get these. Okay, so the Antarctic plate, we've got oceanic. Here's a little bit of continent, 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 continent. But remember, the continent is round because we know Antarctica is round. So now we've got one plate, the Antarctic plate. The next plate I'm going to show you is the largest one. This is the Pacific plate, which is pretty much all oceanic crust. It's the Pacific Ocean, and we're going to put it in right here. Okay, let me get it adjusted right. There we go. So now we've got 2, Antarctica and the Pacific plate. The next one we're going to do, this one's going to be 2 plates at one time, and I'll explain why. So we've got the North American plate, and we've got the South American plate. There is a major fault kind of thing going through here, but it's so convoluted. I decided we won't cut this particular puzzle piece here because it's not a real solid plate boundary that's easy to follow. So we're just going to count this as 2 plates, North America and South America. And we're going to get those into here. So now we've got 4 plates, and Africa's next. And as you're looking at this, you see there's continent and there's oceanic. This is one plate, but with 2 major differences. One is the continent, which is made up of igneous sedimentary metamorphic rocks, and the ocean plate, which is pretty much all basaltic, which is volcanic. And that's important because this is much denser than this. All right, let's put Africa in. Okay, hope it's going to stay up here. All right, now the next plate is the Eurasian plate. All right, so that's Europe and Asia. They kind of ran into each other. They formed one huge plate called the Eurasian plate. And that's going to go right there. All right, now, how many plates do we have? 1, 2, 3, 4, 5, 6, the last plate. And that plate is called the Indo-Australian plate. And let me get the right puzzle piece here. Okay, Australia. Here's Australia. Whoops, I think it's going this way. Here's Australia. And here is India. India and Australia, you know, the map's broken up into 2 different places. So it's one plate that kind of is shaped like this. But because we have a 2-dimensional map and not a globe, I had to split these pieces, and one's going to go on one side of the map and the other's on the other. Here is India, and here is Australia. So let's get Australia in. Whoops, Australia's on this one here. And then India is next to it. Oh no! All right, don't worry, we're going to get it back up. You know, I haven't had a problem with it falling down yet, except when I created an earthquake. And this was not an earthquake. I think the puzzle pieces are protesting as to the angle that I've got them at. We'll see if we can make it work. All right, get in India right here. There we go. This plate, it's a small plate. It's called the Nazca plate, and it's a pretty crucial plate. See if we can get it in. There we go. And then this is the rest of the Eurasian plate way over here. And I'm not going to test my luck with this map right now, so we're going to put it over here. Okay, but it's the rest. And look, it's all convoluted in here. Now, when you're looking at this, what do you think the red arrows represent? Put it in your chat box. What do you think the red arrows represent? Okay. Molly, do we have any answers on the red arrows?
We have movement.
Aha, absolutely
shifting,
right.
Movement
Excellent.
of crust. Some good answers.
Yes, some very good answers. Thank you. I was floundering for my chat box there. Okay, so you've got the red arrows and the long arrows. What do you think? The long arrows versus the short arrows. What's the difference? Why is there a difference? Got any ideas?
Are the long arrows bigger?
Oh, yeah, look at that. High velocity. You're right. So the long arrows mean it's moving a lot faster. So the Pacific plate, it's moving pretty fast. Oh, about 10 centimeters a year, which is about an inch a year. Okay, doesn't seem very fast, but it is fast according, geologic wise and plate wise. And South America, it's moving pretty slow. It's a very short arrow, and it's moving northward. And Africa's moving towards Eurasia. Look, this whole continent's moving this way, this whole plate, and North America's moving this way. So all these things are going in different directions at different speeds. And you can see all these boundaries around where the plates are. Okay, so we've got a lot of different boundaries here, and I want to show you a demonstration that kind of talks about those different boundaries so you get a better sense of what the boundaries are and what's happening at those boundaries. Okay, so I'm going to move my camera, and if you got some of your ingredients so you could do the activity along with me, this would be a great time to get them. And set this up here. We're going to pull out our ingredients and we're going to talk about plate boundaries. Plate boundaries. Okay, so what I need, got peanut butter, or you might have some frosting. That's great too. Peanut butter or frosting. And I've got a little dish of water. Put the water over here. And then I've got a tray, and on the tray I have some wax paper. The wax paper is a really good idea because otherwise it'll make a big mess. So if you've got your wax paper and then the peanut butter and the graham crackers, I think we're ready to try it. We are going to create 2 layers of our Earth, the asthenosphere and the lithosphere. So the asthenosphere, remember that's the layer that's kind of flexible, mobile, plastic. Okay, I'm going to stir my peanut butter up a little bit. And now I'm going to put peanut butter. If you got frosting, use frosting. Put peanut butter down on my wax paper, kind of spreading it out. I want it, the area it covers to be bigger than the area of 1 graham cracker, okay? So I'm spreading it out. Oh, I've got to make it a little longer. I can see that. Spreading it out. Yep, spreading it a little bit thicker and a little bit longer. Okay, so it's going to kind of look something like this. Okay, I'm going to check it to see if it's the right length. Get my graham cracker. I want it to be all the way around my graham cracker. And I might spread it just a little bit more, just down here a little bit and up here, just so we can make sure we see what we want to see. Okay, that is my asthenosphere. All right, so asthenosphere is mobile, flexible, plexi, soft, not rigid. That's really important. This graham cracker is going to be my lithosphere. And we're going to break the graham cracker in half. Now, there's kind of a little bit of a line here, so I'm going to aim for that. Break it in half. Oh, good, it worked. And I just created an earthquake. My plate broke. So now I've got 2 plates. And we're going to put one of these plates on top of the asthenosphere and then just gently move it around. And you can see how it moves around pretty easily on this asthenosphere. Okay, now we're going to put the other plate on and we're going to talk about our first plate boundary. Okay, putting these 2 together, they're next to each other. And the first type of boundary is called a divergent boundary. That's when 2 plates separate. You got 1 plate here, 1 plate here, and they're separating. So let's separate our plates. Okay, I'm separating them slowly, slowly. Ooh, and I can see a asthenosphere, and that asthenosphere, actually what it is, it's magma coming up out of this crack between the 2 plates. And when that magma comes up, it becomes lava, it hits the ocean. Oh, I forgot to tell you, most of the boundaries are in the ocean floor. So when that lava hits the water, it cools rapidly, forming a basalt, a rock, a hard rock. And over millions of years, it forms a mountain on the floor of the ocean. Let me show you a video, or it's an animation. It'll just take a minute, but I think it'll help you understand a little bit more about what's going on with this ocean floor here. Okay, so I'm going to start this and I'm going to advance it a little bit so that we don't have to spend so much time waiting for the good stuff to happen. Okay, so as you can see, the plates are separating and the hot magma from the asthenosphere is coming up, pouring out onto the ocean floor, and it becomes lava, it becomes hard rock. And over millions of years, that rock is going to form a mountain. Okay, excellent. So that is 1 plate boundary. And now we are going to go to another type of plate boundary. All right, this one's called a transform boundary. Transform is when you have 2 plates, one's going one way and one's going the other way. So put your 2 plates back together. And we're going to have 1 plate going one direction and 1 going the other. You're going to kind of move them slowly, and you're going to notice that it kind of sticks a little bit, and that's what happens. It sticks, and then all of a sudden it releases, and you get an earthquake. Okay, so now we're pushing it a little bit more. Oh, it's sticking again, and now we get another earthquake. So as they're going, they're grinding along, they're going past each other, and they stick, and it releases. And that's when the earthquake happens. So this type of boundary is seen in California. There's other places too, but California is a good one. It's the San Andreas Fault, which most of you have probably heard of, the San Andreas Fault. So this is a transform boundary, and we don't see any volcanoes here, just earthquakes. With a divergent boundary, you'd see lots of volcanic action, but you also have some earthquakes going on too. All right, so that's two different plate boundaries. A third plate boundary. What if two plates come together? What's going to happen then? Now there's two different ways that this can happen. We're going to take our two plates back here and get them back together. Okay, we're going to get them back together, kind of sticking a little bit on my peanut butter. There we go. We're going to get them back together. Now, if you have two plates, do you remember when I showed you the puzzle pieces? There was plates, like the Africa plate had lots of oceanic crust and continental crust, and South America did, and North America, all the continents, or all the plates except for Antarctica, had both oceanic crust and continental crust. And you remember I told you that the oceanic crust is dense, it's heavy. So when it comes up to a plate that's a continental plate, it's going to dive underneath because it's heavier. It's going to go underneath the continental plate and angle downward. And we're going to do that with our plates down here. So I'm going to just tilt up on one side slightly to push down, and so my oceanic plate can go underneath my continental plate. And I'll probably go in maybe half an inch or so, because then what happens on the plates on the earth, it goes in a ways and then it starts diving down deeper. And as it's diving down deeper, this rock down here is melting. And then that rock comes up and forms volcanoes. And so the volcanoes would form here just past where the two plates had met. And what else is happening? At the same time, you got these volcanoes going on. This plate that's diving down, it gets stuck, okay? And it gets stuck, and it gets stuck, and then all of a sudden it releases, and you get mega earthquake. I've got a good video of that, or a good animation of that. Let me pull that up for you. Okay. All right, there's the transform boundary, and all right, here it's going. See the oceanic plate? It's going down. That yellow line is where it's going to get stuck. The oceanic plate's getting stuck. Actually, it's more the upper plate that's stuck. The oceanic plate is still going down. Look how the continent's getting taller and the water's getting deeper. It's getting stuck, and pretty soon it's going to release in a giant earthquake, and then you're going to see things kind of settle back. Did you see those waves going out? In earthquake, when it happens, waves go out. Vibrations. The earth is vibrating and it generates these waves that go way out. Okay, and that's called subduction. When one plate goes underneath the other, those earthquakes are some of the biggest in the world when that happens, because it really gets stuck for quite a long time and then releases. And the other thing that happens with subduction ones is you can often generate tsunamis because there's water, the ocean's right there. So these are one of the most dangerous ones, the subduction earthquakes, or the subduction boundaries. Okay, now we've got one more. What if the two continents come together and they're both the same density? I'm going to get two different crackers. So I'm going to move these out of the way, and I think I'm going to have to smear some of my asthenosphere back over here so we get some good asthenosphere going on here. All right. And I'm going to get another cracker. I've already broken this cracker. You've got to break it again. So we've got two plates once again. But now we're not putting it on the asthenosphere yet. We're going to dip it in water. Really a quick dip. And I'm just going about half an inch or so. So dip it in and put it onto my asthenosphere. And I'm going to do the same thing with my other one. Dip it in and put it onto my asthenosphere. Okay, now I've got my two plates, two continental crust plates coming together, and now we're going to push them, push them together. Oh, look what's happening. It's forming a mountain. Can you see that? It's forming a mountain. And that's the plates that we have, the Himalaya Mountains. India, the plate continent of India plowed into Asia, forming the Himalaya Mountains. Okay, so we've got these 4 different types of boundaries, and I want to show you, I'm going to show you one more image here. Okay, look at where all of the earthquakes and volcanoes are around the world. What do you notice where all those are located? Put it in the chat box. All those are located. What do you notice? Okay, I got to get the chat box. Molly, can you tell me what they're coming up with?
We have some suggestions at the plate boundaries,
Yeah.
where the plates meet, where the arrows on your map were pointing.
Yeah, absolutely. So when they started plotting these on a map, they realized plate tectonic, this whole idea was absolutely on the mark. Okay, so looking back at our map here, all right, the Mid-Atlantic Ridge. Does anybody remember when what's a divergent boundary? What's happening? Okay, I'm going to see if I can see it in the chat here. Where the plates meet. Ah, the divergent is the opposite. It's where the plates, oh, you were answering the other question.
Yeah.
Divergent is when the plates separate. And the best place in the world to see that is the Mid-Atlantic Ridge. This whole ridge is full of volcanoes and mountain ranges all along there. And there's some earthquakes happening too. All right, we talked about another one, the transform boundary. Do you remember what the transform boundary does? Anybody got any ideas? Transform boundary.
Let's see.
Yeah, the plates, the divergent is where the plates move apart, and the transform where the plates, yeah, they're next to each other. Good job, next to each other. And that's San Andreas Fault. And the San Andreas Fault is right in here. And this map doesn't show the scale, but there's there's another little plate in here. And so one plate is going northwest and one plate is going southeast. And that's what's causing the friction and the faults along the San Andreas Fault. Okay? And they're pretty dangerous. But the third boundary type is the most dangerous. That's the subduction. And the subduction zone, where you've got the 2 plates and one's diving down the other because it's denser. The oceanic plate dives down. And in North America, actually, it's happening in a lot of places, but in North America, there's a little plate right down here called the Lafarion plate. It was much larger. Most of it has already gone down underneath North America. It's melted, and some of it's come back up in the form of volcanoes. Mount St. Helens, Mount Shasta, the whole range of volcanoes in here, because of this tiny little plate, which was much bigger, is diving down underneath. And as it's diving, remember I told you, as it dives, it gets stuck. You saw that in the animation, and you can create an earthquake. Those are the biggest earthquakes that happen. They're huge. Okay, so they've prepared. I don't know if they're real prepared, but I know they've talked about Washington and Oregon in particular. They've got all kinds of drills and things that they have practiced. They've got earthquake necessities, earthquake kits. So they're prepared, which is good. It's going to happen. Now, is it going to happen when I'm alive or you're alive? I don't know. Geologic time. It's an immense, immense time. But if you look at all around what we call the Pacific Ring of Fire, the Pacific Ring or the Ring of Fire, this whole plate is moving. It's oceanic, so it is going down underneath these other plates, And as it does, it's creating huge earthquakes. Japan has had some big earthquakes. Indonesia's had some big earthquakes. Actually, over here too, Chile and Argentina, or Chile and Peru have had some major earthquakes because this one's moving down. So this is sort of the ring of fire because of the volcanoes and the earthquakes that happen here. Well, and then our last boundary where the two come together and they're the same material, continental, the Himalayan mountains here in India and India continent plowing into the Asian continent. Okay, so how do we know all this? Well, we've got instruments that can measure the earth and measure the waves that happen in the earth. So let me set up, I want to show you some of the waves that we can do, we can see. They've got something they call a seismometer. A seismometer is a machine that will measure the waves, the vibrations in the earth. Okay, so first I'm going to show you the waves that can be generated. When an earthquake happens, there's basically two waves, and those vibrations go through the earth, okay? All the way through the earth, and we have seismometers that measure that. And that's how they figure out, oh, you know, how big it is. If it depends on the seismometer and the graph that reads out. It can tell how long it is. You get a number of these seismometers, and we have a lot of them. You get a number of them, and they can pinpoint where the center, the focus of the earthquake was. Where did it start? All right, so two different types of waves. Okay, so Molly, you're going to have to let me know if you can't see this real well, okay? Because I'll try a different angle. But I'm using a slinky. If you've got a slinky, you might be able to do this too. So one wave is a P wave. That it's called a compression wave or a P wave. And it just kind of goes straight. It's going to go this way, and it's going to go this way, and it's going to go this way. It goes off in all these different directions. And basically, one molecule, one atom hits another and hits another, and it just progresses and moves along. So I'm going to pretend my earthquake is happening right here. See if I can do this. And you're going to kind of watch to see the bump going through here. Okay, ready? Here it goes. P wave, earthquake. Did you see it? Okay, do it again. How's that? Did you see it, Molly?
Yeah, it looks good.
Oh, good, good. You can see it. It's basically you're seeing the light shining off of it, but you can see the wave is going along. There's another one, and another one, and another one. Yeah. Okay, the P waves are going through. Earthquake, earthquake, earthquake. And you know, there's always a major earthquake and then little ones afterwards. Okay, now we're going to do the other kind of wave. The other kind of wave is called an S wave, and it kind of forms a serpentine shape, an S shape. And it's going to go through, okay, I'm going to start my earthquake again. And it's going, and it's forming this S shape. And look, I'm creating a pretty long earthquake. The longer it shakes, the longer the wave goes. Okay, so that's the S wave. And then we've got the P wave going like that. These waves can be detected on a seismometer. Now, of course, if you're close to the earthquake, you're going to feel it, okay? But if you're not close to an earthquake, you can't feel it, but the seismometer can detect it. These waves go through the earth, and they go all the way through the earth. So if something happens in Japan, we can detect it with our seismometers here in the United States. And there is something called a sudden motion sensor that is visible or is in iPads and old iMac computers and in your iPhone, and you can download basically a seismometer. Okay, so I'm going to move this a little bit closer and then set up my camera so hopefully you can see my seismometer. So Molly, you're going to have to let me know if this is visible or not. If that's, whoops, not yet. Okay, let's see, I need to go like that. How's that?
That looks great. Oh,
Does it look good? Okay.
it got a little bright actually.
Oh,
If you
yeah,
go
that's
up just
because
a little
cameras
more,
and the white light, that's not much I can do about it.
can you
But
angle
there
it
is,
up?
angle it
Try
up.
just a little smidge.
How's that?
That's a little better. Is there a way to do a little more?
Yeah. No, this is good. How's that?
That's closer. I think we're really
Okay.
close. Yeah, I think we can see that there.
Okay, there's a line. You may not be able to see this, but watch what happens, except I'm going to take a puzzle piece off. Otherwise, I lose my puzzle when I create an earthquake. Okay, I'm going to try taking it. I'm creating an earthquake, and I'm going to hit the table, and my seismometer is going to read the vibrations. Ready? Here we go. Okay, can you see it? There's a
Not
big bump right
quite.
there. Not quite. Okay, let me move it a little closer. And okay, and let me try it again. All right, here we go. One more time. How's
Oh
that?
yeah, we can see that one.
Oh, good, 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 good. Okay, because I've got a puzzle on, I think we'll just go with that so I don't lose the whole puzzle. And let me move back to our puzzle. And did we have any questions, Molly, that were coming up? All right, here we
I
go.
haven't seen any questions. So this is a good
Okay.
chance to remind everyone, if you have any last questions for Cindy, feel free to put them in the chat box. She'll be able to
Yeah.
answer them.
And also you can go to our webpage, and there's a really cool activity that you can do. Challenge yourself, be like Professor Wegner, and see if you can recreate the evidence that he did for what he was calling continental drift, but actually supports plate tectonics as well. Okay, so reviewing, there's 4 different types of plate boundaries, and we can see how wonderfully these plate boundaries are mirrored with the volcanic and earthquake action we see around the world. And it's all thanks to this wonderful asthenosphere that we have in the, not in the center of the earth, in the, just beneath the lithosphere. You know, one thing I forgot to mention is that we know that the outer core is liquid because those S waves, they were watching, looking at these seismographs, and they realized what happens to the S waves? They just stop. And so they started doing some more experimenting, playing around with S waves and P waves, and they discovered that S waves cannot go through liquid. So they stop when they get to the core. Now the P waves go right on through. They can go through solids and liquids, but the S waves can't. So that's how they came to the realization that the outer core is actually liquid. Kind of cool.
And Cindy, we have one good question here. Where can we get a puzzle like yours? That thing is awesome.
It is awesome, isn't it? Well, I'm afraid it's a special puzzle that the museum made just for me years ago. I am a geologist, and I do like geology. And so, you know, last month and this month, I've had a lot of fun sharing some geology with everybody. And
I bet that you could take a map and cut it up
oh, you
and make a puzzle
could.
yourself.
That's a great idea. Yeah, you could glue it to some kind of foam core. That's what ours is on, is kind of a foam core. I wonder, maybe we should make these and sell them in the gift shop. That might be a fun thing to do. What a great question. There's something else that came in.
So what you're saying is that we should
Oh,
come work with you. Sounds great.
I think so. We have a great job. I learned so much with this job, but I do like sharing geology the most. Well, I hope you had fun with us. We have several things coming up. Tuesday, go to our website, and we have registration. It's free, of course, and you can do a virtual field trip either at 10, 12, or noon. I'm saying it wrong, 10, 12, or 2. And it's Art of Sea Monsters. We'll be in our Mesozoic gallery, and the Mesozoic gallery will have Annie is going to be doing, I'm going to pull up our website here. Annie is going to be doing that program. And I think it's a 45-minute program. It's really fun. You get to create your own mural at the end of it. So check that out. You do need to register just so you can get the link and we can have safety with numbers and stuff, making sure we don't get, what's it called, Zoom bombed. And let's see, what else is coming up? Oh, there's story time. Isn't there story time later this week, Molly?
Yeah, we have story time on Thursday at 4. And so we'll be learning about insects and reading some stories and doing some little activities to go along with that.
Excellent, excellent. And we haven't quite decided on the Saturday Investigate for June. So if you got any ideas, you might throw them out to us. We'll see. At least I haven't heard of anything. They could have something going afoot that I'm unaware of. So we're really glad you joined us. We miss you guys at the museum a lot because I know we have some regulars who come every second Saturday to check us out. And I hope that it won't be too long before we see you in the museum. But for now, I'm glad you're joining us. All right. Goodbye, everybody.
Yes, thank you, everyone. And thank you to Cindy, of course, for today's wonderful program for Saturday Investigate. We hope that you all enjoyed the program today. And again, you can find the activity guides on the museum's website, along with videos and other activities that you can enjoy from home. There are lots of other things happening at the museum, so definitely check it out. And we'll see you next time. Thanks so much again for joining us.